Welcome to this special episode of the Luminous podcast series, where we explore cutting edge innovation in language augmented extended reality. Today, we're diving into Deliverable D3.1, the first demonstration of pre trained grounding models for instruction generation. This work package, WP3, is part of the Luminous initiative, Language Augmentation for Humanverse, a Horizon Europe project pushing the boundaries of human-computer interaction through next-generation extended reality systems. In this demo, we showcase our initial implementation of models designed to bridge the gap between perception and action, enabling systems to understand complex environments and generate natural language instructions grounded in real-world contexts. From aligning visual scenes with textual commands to enabling interactive, intuitive guidance in XR applications, this milestone lays the foundation for intelligent, adaptive instruction generation. Funded under the European Commission's Horizon CL for 2023, Human 121 call, Luminous, is shaping the future of extended reality. It is a research and innovation action. Stay tuned as we walk you through the demonstration and key insights from this early version of D3.1. Let's get started. Look at this complex real-world scene. It contains a variety of everyday objects like a coffee machine, mugs, grinders, a water bottle, and even a tripod. In such a setting, many different actions can take place. For example, someone might want to make coffee, clean the counter, refill the water tank, or simply grab a mug to drink water. To be truly useful, AI systems must be grounded in these kinds of real-world environments. They need to understand both the objects and the situational context in order to provide accurate, contextually relevant, step-by-step instructions in response to user queries. To solve complex real-world scenarios like the one we just saw, the first step is grounding, understanding what objects are present and how they relate to one another. We begin by passing the image of the scene through a vision language model, or VLM. The VLM analyzes the visual content and identifies all relevant entities, like the coffee machine, mugs, glasses, containers, and more. But it doesn't stop at object detection. The model also extracts rich attributes, such as color, size, material, and state, and captures spatial and functional relationships between objects. For instance, the mug is on the shelf, or the person is holding a towel. All of this information is structured into a scene graph, a formal representation that maps objects, their properties, and their relationships in the environment. This graph becomes the foundation for generating grounded, context-aware instructions. By building this scene graph, we give AI systems a concrete understanding of the physical world they are reasoning about. Once we build the scene graph, the next step is to convert it into a standardized language representation. It is important to note that to identify instances of objects, we append the instance ID to the object name. Therefore, we refer to a table as Object Table 1. While the raw scene graph captures rich visual and relational information, it isn't immediately interpretable by large language models. To bridge this gap, we parse the graph into a structured, text-based format that follows a standardized schema. This standardized scene graph language clearly describes each object, its attributes, and the relationships in a consistent, readable form. For example, Object Mug 1 standing on Object Table 1. By doing so, we ensure that language models can better understand and reason over the visual structure of the scene, enabling more accurate and grounded instruction generation. Once we have the standardized scene graph, we tailor it to the specific task at hand. This step is crucial because not every object or relationship in the scene is relevant for every situation. For example, imagine the user asks, "How do I make a cup of coffee?" To answer this, the AI doesn't need to consider unrelated objects like the tripod or the towel. Instead, we prune the scene graph to focus only on relevant elements, such as the coffee machine, the mug, the grinder, and the person. By using this scenario as input, we automatically construct a pruned scene graph that captures only the subset of objects and relationships needed for the current task. This makes the reasoning process more efficient and helps the language model generate precise, focused instructions grounded in the actual context. With the pruned scene graph and a natural language scenario prompt, we are now ready to generate instructions. In this example, the user says, "I want to drink coffee." This prompt, along with the relevant contextual information from the pruned scene graph, is provided as input to a large language model. We apply this setup across both our base models, such as pre-trained LLaMA, and our fine-tuned models trained on our custom dataset. The model is tasked with producing situational instructions, clear, actionable, and grounded steps that are tailored to both the user's goal and the current environment. This setup allows us to evaluate how well a model can reason about the physical world and generate useful instructions based on real-world context, not just text. Here, we present the output from a non-fine-tuned base language model when given the scenario prompt and the pruned scene graph. Immediately, we notice two major issues. First, hallucinations. The model incorrectly assumes that the person in the scene is wearing gloves and uses that assumption to justify an action. However, the scene graph never mentions gloves, and looking back at the original image from slide 2, we can clearly see that the person isn't wearing any. This hallucination is highlighted in the red box. Second, we observe overflow. The model generates excessively verbose and often unnecessary instructions. It goes beyond what is required for the task, making the output less clear and more cumbersome. This overflow is shown in the orange box. These issues highlight the limitations of relying on base models that haven't been adapted to grounded, context-aware reasoning. As we observed in previous slide, standard language models struggle to generate reliable instructions out of the box. They tend to hallucinate and produce overly verbose outputs. To address this, we created SAD, the Situational Aware Dataset, a carefully curated dataset that aligns visual context with scenario-specific, grounded instructions. This slide outlines the data generation pipeline for SAD. In step 1, we begin with a complete scene graph and generate multiple scenario descriptions using a scenario LLM. Each scenario is then paired with a pruned version of the scene graph, filtered to include only task-relevant objects and relationships. Human evaluators review and refine these pairs to ensure accuracy and relevance. In step 2, we generate detailed instructions using a humanoid-like LLM that interacts with the scene graph through a QA-style session. This allows the model to reason through the scenario, asking clarifying questions if needed. Finally, in step 3, we use a summarizer LLM to condense the full instruction trace into a clear, step-by-step list that is easy to follow. This structured pipeline ensures high-quality, situationally grounded instruction examples, paving the way for fine-tuning models that perform more reliably in real-world contexts. This slide presents a concrete example of how we generate entries for the SAD, Situational Aware Dataset. We begin with a visual scene and a clear scenario prompt. Make exactly 1 cup of coffee. The LLM, grounded in the scene graph, produces a detailed set of step-by-step instructions tailored to that scenario, but we don't stop there. A question-answering loop is initiated to clarify vague or underspecified steps. We have 2 LLMs. The first is the oracle that generates instructions, and the second asks clarifying questions in order to avoid ambiguous instructions. This loop is fully automated. For instance, the model initially mentions grinding the coffee beans to an appropriate consistency. The clarifying LLM asks for clarification, and the oracle responds with a refined answer. A fine grind consistency, resembling granulated table salt. This interactive QA process ensures that instructions are not only grounded and relevant, but also precise and easy to follow. Finally, the refined steps are passed through a summarizer, LLM, to produce the final clean instruction list, ready for use in training or evaluation. This multi-step pipeline is what makes the situational aware dataset unique. It's not just about generating instructions, it's about making them truly situationally aware. This slide provides an overview of the structure of the SAD Instruct dataset, which is designed to fine-tune models for situational instruction generation. The dataset includes a variety of input-output pairs that reflect realistic interactions between users and an AI assistant grounded in a visual scene. On the left in blue, we see samples from robot oracle conversations. These include a scenario prompt, follow-up clarifications, and summarizations. For instance, a user might ask, What steps should I follow to do task S? Or follow up with, can you explain step 3 in more detail? The model responds with detailed instructions and clarifications, just as a helpful assistant would. On the right, we see scene graph reasoning tasks. The green boxes handle positive pruning, figuring out which objects are needed for a task. The red boxes handle negative pruning, identifying which objects are irrelevant. The orange boxes focus on instruction generation from partial graphs, helping the model reason even when it has only limited context. By including this diversity of tasks, the SAD Instruct dataset enables LLMs to understand what is relevant, ask or answer clarifying questions, and ultimately produce clear, grounded, and actionable step-by-step instructions. This slide summarizes the key statistics of our situational instruction dataset. Our dataset spans a total of 1,482 unique scans from indoor environments. These scans give rise to 6,927 scenarios, each reflecting a distinct task grounded in a real-world scene. Out of these, 5,519 scenarios are used for training, while 1,408 are reserved for testing and evaluation. In total, the dataset includes more than 163,000 detailed task steps, offering rich and diverse examples of how instructions should be generated across various contexts. From a language modeling perspective, the dataset comprises nearly 89 million input tokens and over 6 million output tokens, totaling more than 95 million tokens. This makes SAD not only high in quality, but also large enough in scale to meaningfully fine-tune and evaluate instruction-following models. These comprehensive statistics reflect the depth and rigor of the dataset, making it a strong foundation for advancing grounded instruction generation. Here we demonstrate the performance of our fine-tuned LLM, trained on the SAD dataset. Given the same scenario, I want to drink coffee, and the same pruned scene graph, we now see a significantly improved output compared to the base model. The fine-tuned model generates clear, structured, and grounded instructions that reflect an understanding of both the task and the environment. Importantly, it avoids hallucinations. For example, instead of inventing gloves like the non-fine-tuned model, this version correctly refers to grasping the cup with both hands, which is both general and visually plausible.